Hello friends, welcome to follow up. Let's revisit problem 2685. Count the number of complete components. In the previous video, we explained a solution based on traversal algorithms. In this video, we're going to explain a solution based on union find. So this problem gives us a graph. So we want to find the complete connected components. So the return for this problem is the number of complete connected components. So here we have two examples. In the first example, the return is 3. So all the 3 connected components are complete. So here it's good to notice the single node connected component 5. It's regarded as complete. So in the second example, we know the connected component containing nodes 3, 4, 5 is not complete. For example, there's no direct edge between nodes 5 and 4. So the constraints for this problem are basically first one is on the number of nodes, which is bounded above by 50, and the number of edges is bounded above by the combination number Cn2. In other words, choose 2 out of m. So the others are basically consistent assumptions. For example, we can notice that there's no self edges and also there's no repeated edges. So with that said, basically we can directly go to the coding part. So here, let me first write some annotations or remarks. First, here the method. So we're going to use is union find method. So this also, the corresponding diff structure is called disjoint set. So here our plan or outline is the following. First, I'm going to implement union find. So basically, we are going to expose to you the union and find methods, and also we are going to write a utility function to get the number of connected components. So this is the first step. The second step is basically problem logic. So we're going to call the union methods to incorporate the problem logic with the data structure. And the third one is a utility function to check completeness. And lastly, so we're going to do the return. So this is our overall plan. So as you can see, we split the coding into different ingredients. So the motivation behind is that we want to expose the overall structure in a organized or clear fashion. So with that said, let's look at the coding. So in between, we're going to explain the logic. So the first part, basically, we want to implement union find. So in this problem, the number of nodes is already given. So we can do this without writing a separate class. So we can do this I and see I for I in range n, right? So here, originally we set each node has itself as its parents or root. And then we're going to have a rec. So here we are going to set rec to be 1 for each node, indicating that the size is 1 or just the node itself. So then we're going to implement 3 methods. The first method is find. And the second method, so we're going to implement is union. The union will accept 2 arguments. So, and the last one we're going to implement is called get clusters. So it accepts no arguments. So this is the first step. So the second step is going to call on this union method and incorporate with the problem logic. And now let's first focus on implement these 3 functions, which is actually very routine. So first, I'm going to initialize a variable called result inside the function. And then we're going to check if result and the roots are the same or not. If the same, we're going to return. Otherwise, we're going to retrieve above the chain. So we're going to set the result to be root result. So basically, we can return result. So this is the vanilla fand function. So actually we can also accelerate this function a little bit by using path compression. So we are going to accept the root to both sides. So in plain English, so we are going to set the result, and the root of the result to be the root and of the root of result, right? So this is the so-called path compression. So this actually accelerates the cluster representation retrieval, right? So this is the find method. Now let's look at the union method. So here I'm going to implement the union with union by rank. So first I'm going to get the roots, right? Root I, root j. We can use the find I, and find j. So if root I equals root j, basically it means the I and j are in the same cluster. We do nothing. If they're not the same, root j. What we are going to do is to reset the roots and then adjust the rank. So first, if rank root I is no less than that of root j, then we're going to set the root of root j to be root I, right? This corresponding to combine the two clusters. So afterwards, so we add the cluster size together. So we're going to increment the rank of root I by that of root j. So otherwise, so if rank of root j is larger, so we are going to do the same thing, but in the reverse direction. So we're going to do this, and we change this j to be I and I to be j. So similarly, we are going to increment the rank of root j by that of rank I. So this is the union operation. So for the problem logic here, we need to implement the getCluster function, right? So for that, let's do this. So this is the very routine. So we're going to return this in terms of a dictionary, right? The dictionary key will be the representation of the corresponding cluster, and the value will be the nodes in that cluster. So here we are going to iterate for node and parent in root items. Then first we find the root, that is find p, right? Then we're going to do the check if r not in D. So we're going to set dr equals a set which containing the node itself. Otherwise, r is already in D, so we're going to add the current node to the cluster represented by r, right? And finally, we are going to return D. So actually, we can return the values of this dictionary. The values actually corresponding to the clusters. But now let's content ourselves with this return. So this is the first part. So though this code, if you count the lines, actually is sort of long in a sense, but it's very routine. So now the second step is the problem logic. So for the problem logic, what we are going to do is the following. So first we are going to do the union operations for UV in edges. So we are going to do union UV. So you can do union VU. Actually, from the way we write the union function, you can see actually it's sort of symmetric, right? The overall effect is equivalent. So then after this, we can get the clusters. So the clusters will be get clusters. So we call this function above, and then we're going to retrieve the values, because the values are the corresponding clusters or the set of nodes in that cluster. So we are not interested in the representation or delegate. So with that said, so we need another function. So the third part, that is, we want to write a utility function to check completeness. Let me copy this line here. For this, basically, first I'm going to do such a thing, graph edges. So I'm going to use a dictionary. I'm going to typify the edge, right? For edge in edges. Then we want to check for the nodes in each cluster, so to see if it's complete or not. So let me write a utility function like this: complete C. So C is a cluster, in other words, a set in this problem here. Then basically we just check. Let's write in a very rough fashion. For I in C, for J in C, if J equals I, so we're going to continue, right? Otherwise, if we're going to check if ij not in graph edges, right? And so here, let's see. And so because this is the two directional, we are going to check also gi. Gi also not in the edges, right? It means it's not complete, so we're going to return 0, so not 9. So after the for loop, so we're going to return 1, means complete. So this is the one way. But basically, if you do not want to check or just want to check one condition, you can add the reversed edge, because here, for example, edge is ij. You can also add gi in the graph edges in the set. So that way you just need to check 1. But if you do not want to do that add, so you can do 2 check here, check the 2 directions, right? So that's the utility function. So now let's look at the fourth step, that is return, right? So do the return. So here let's use comprehension again. So we're going to check complete for a cluster, in clusters here, right? Let's copy this part. That's actually the full solution code. So before we make any comments, let's first do a check. Yeah, it passes the first example. Now let's look at the generic case. Yeah, it passes all the generic cases. So I guess that's about it for this specific problem. As we mentioned, because this problem involves finding connected components, basically there are 2 typical ways. One is using traversal. One is using the unit find here. So you can also practice a solution using traversal. With that said, that's about it for this video.